all me?
Yeah.
All me, but me on the board.
Yeah.
Okay,
You're
ready?
I'm starting.
Now. Okay, howdy. Sorry that I'm not with you guys this week, but we're gonna go ahead and cover some of the lecture material that we would have covered in class on Tuesday. So we're gonna start where we left off last week. And we left off last week talking about enthalpy, which is the change in energy. And if you remember from last week, we always represent enthalpy as delta H, okay? Now, I just want to do a little bit of a review about our change in enthalpy. Now, we have two kinds of reactions. One reaction is an exothermic reaction, and that means it gives off heat. Okay, here's an example of an exothermic reaction. Hydrochloric acid and sodium hydroxide will yield water and sodium chloride and energy. Okay? Last week we talked about the fact that when we have an exothermic reaction, we're going to go ahead and include our energy as a reactant in the chemical reaction. If we're talking about an endothermic reaction, that's a reaction that absorbs heat. Here's an example of an endothermic reaction. Water plus sodium chloride plus energy yields hydrochloric acid and sodium hydroxide. Okay? When we have an endothermic reaction, we're always going to list our delta H, or our enthalpy, which is our change in energy, as a reactant. So in an exothermic reaction, it's a product. It's one of the products. Did I say reactant before? Oh, sorry. I said reactant. I meant product. It's a product in an exothermic reaction, and it is a reactant in an endothermic reaction. Now, one other thing I want to make sure we understand is that when we calculate a change in enthalpy, we're going to get either a positive or a negative number. And that is because of the manner in which our calculations have been set up. The reason that we get a positive or a negative number is so that we can easily identify whether we've got an endothermic reaction or an exothermic reaction. However, okay, so a calculated change in enthalpy in an exothermic reaction is going to be negative. A calculated enthalpy, change in energy, in an endothermic reaction is going to be positive. Okay? However, when you list it in the chemical reaction, you're always going to list it as a positive number. So whether you have, when you're dealing with enthalpy, change in energy, as a stoichiometric equivalent, you're always going to list it as a positive. So for example, let's say, for example, that this particular exothermic reaction has a delta H, a change in energy. It gives off, let's just say it's 1200 kilojoules per mole, okay? So when if we were to calculate this number, we would get a delta H equal to negative 1200 kilojoules per mole, okay? When we add this into the equation, we would write it up here as a stoichiometric equivalent as positive 1200 kilojoules per mole. And again, the reason why we're going to make it positive is so that we're not dealing with a bunch of negatives in our stoichiometry. We set it up to be positive or negative in the calculation of the actual enthalpy, so we know whether it's an exothermic reaction or an endothermic reaction. Likewise, for this bottom reaction, if we had a delta H for this one, we would have a delta H equal to positive 1200 kilojoules per mole. All right, and we would list it right here as a stoichiometric equivalent as 1200 kilojoules per mole. Now, once we have this number in our chemical reaction, you use it just like any other stoichiometric equivalent. Well, what do I mean by that? Well, let's say, for example, that you had a situation where you knew that you ended up with, in an actual experiment, 2 moles of sodium chloride. Okay? And they ask you how much energy is going to be absorbed by that chemical reaction. Well, that's easy to calculate because I know that for every 1 mole, here's my stoichiometric equivalent, for every 1 mole of sodium chloride, I will absorb 1200 kilojoules per mole. Okay? So if they're asking you, if they say, well, I don't have 1 mole, I have 2 moles, how much energy is going to be absorbed? It's just like every other stoichiometric equivalent. 2 moles of sodium chloride times 1200 kilojoules per mole. okay? Or my moles cancel out here. So I would end up with 2,400 kilojoules of energy. Okay, we'll look at that with the practice problems, but that's the idea behind using enthalpy, the change in energy, as a stoichiometric equivalent. Go ahead, pause.
Boop.